So, okay. Yeah. Thanks for joining. We are in week 3, and week three's concept is machine learning with classification. Okay. Um, so in the last week, we discussed about linear regression. Um, can you guys tell how to evaluate a linear regression model? Do you want to answer this question? Um, how do we evaluate a linear regression model? Right? We have primarily discussed about two things. One is root mean squared error, and the other one is R2. Root mean squared error should be equal to 0 for a good linear regression model, right? And I think R2 should be close to 1 for a good linear regression model, right? These are the two things we use to evaluate linear regression model, right? Then, so in the today's lesson, we discuss about data pre-processing, then k nearest neighbor classification, then how to evaluate a classification model. And at last, we discuss about logistic regression. Okay. So let's dive in. So pre-processing. Why do we have to pre-process the data? Right. So the machine learning models understand numerical data. They don't understand categorical data, right? If your input feature is in string, the machine learning model may not able to understand, right? So that's why you need to um, pre-process the data, right? Um, and in pre-processing, we have normalization. That's one type of scaling. So normalization is where, let's say you have different features. One feature is on a scale of 0 to 10. Let's say the second feature is the house price, which is on a scale of 100K to 500K. Then the scales of the two features are different, basically. If you use the data as is to train the model, your model may not be trained well. So you need to scale the data so that it will fit between 0 to 1 in order to get the good model. So this is basically a normalization scaling, which is also called min-max scalar, right? Where we rescale the features so that they fit into range between 0 and 1. And for that, this is the code from scikit-learn, from sklearn, you import min-max scalar, and then your x is the input feature. You pass that to fit underscore transform function, and then you get a scaled feature, right? That is about min-max scaling. And another scaling function is there that's called standardization. So where in standardization, your data is converted such a way that the mean will be 0 and standard deviation is 1, right? And this is the code for standard scalar. right? You create a standard scalar instance and then call fit underscore transform function on your X feature, then you get a scaled feature, right? The scaling we need to do for numerical data, right? So data can be numerical data or categorical data, right? For numerical data, you need to apply scaling. So in scaling, there are two types, as I said. One is normalization, and the second type of scaling is standardization. In normalization, you convert the features so that they fit in the range between 0 and 1. In standardization, you scale the data such a way that the mean is 0 and standard deviation is 1. And let's say your data is categorical data. That means it's not numerical. Let's say it has strings. Let's say this is your data. It is of string objects. Then you have to apply one-hot encoding. As I said, machine learning models can't understand categorical data, which is data of type string. So you need to do one-hot encoding to convert the data of strings to data of some kind of numbers, right? So this is how you do one-hot encoding, right? So this data is converted as this data, right? Here is an example of one-hot encoding. Um, let's say this is cat. It's taken as number 1. For dog, it's taken as number 0. And for tortoise, it's taken as number 0. Whereas for the second row, for dog, it's taken as 1, and rest of the values taken as 0. And for tortoise, it's taken as 1. For the third row, rest of the values are taken as 0, right? This is how one-hot encoding is performed in order to encode your data, right? So this is about pre-processing, scaling and encoding. You apply scaling for numerical data, encoding for categorical data. And one-hot encoding is the technique we discussed for categorical data, right? So yeah, you can see over here, machine learning models understand numbers. So and any questions up to now? Okay. Then feature engineering. I think we discussed in the previous lesson also about feature engineering. So you can create new features from the existing features. Let's say you have a data frame which has weight in kilograms, height in meters, and age, and you want to create one more feature within this data frame, which is called BMI. Then you calculate BMI based out of weight feature and height feature. So this is an example of creating a new feature, right? And the second technique in feature engineering is extracting parts of the feature. Let's say you have a year in the data frame, but you want to create a new feature which tells the day, for that year. Let's say the year is April 17, 2026. But you want to create a new feature which says the day as Friday, right? So that you will further you need to extract parts of the feature. Yeah, sorry. Here we are extracting year from the timestamp, right? So this is one technique to to one technique in feature engineering. You extract parts of the feature, right? Um, and then you can create binning for continuous values. One example you can see over here is the age feature. We are converting it to bins. We are saying the ages between 0 to 20 should be in one bin, 20 to 30 should be in one bin, 30 to 40 should be in one bin, 40 to 100 should be in one bin, right? And we provided labels to the bins. Between 0 to 20, we are providing label as young, right? So that is one type of feature engineering. And then we can create a boolean feature um, based on the age. If the age is greater than 65, then we are treating it as true for a senior, right? Let's say we are creating one more feature. The feature name is senior. If the age is greater than 65, then we are saying is senior is true. Basically, we insert a Boolean feature, Boolean value for is senior feature, right? So this is about creating a Boolean feature. And this is about feature engineering. Okay, just a second. Sorry, I'm sharing again. So that's about feature engineering. Then within pre-processing, we have one more concept called dimensionality reduction with principal component analysis, right? Sometimes, let's say you have a video which consists of hundreds of pixels, and each pixel is a feature, right? And if you want to train your model on hundreds of features, then you require good hardware and it takes time to train the model on hundreds of features, right? So in those scenarios, we can think of how to reduce the number of features from 100 to 2, let's say. If we can reduce from 100 features to 2 features, then the amount of time taken to train the model is reduced, and also our model can well fit the data, right? It won't overfit. If the number of features are small, model will fit perfectly, right? So this is an example or a process of dimensionality reduction. So we are reducing the number of features from 100 or 1000 to 2 features without having an impact on the prediction, right? So you can see over here, there are so many features and we converted to less number of features. And sometimes it's definitely required in machine learning, right? So how do we reduce from 100 features to 2 features? Because those features are correlated, means let's say they're all positively correlated. Then instead of having 50 positively correlated features, you can have one feature to train the model, right? So many real data sets have correlated features. So PCA finds directions of maximum variance. The number of features are reduced to 2 features. So let's say PC1 is one feature, PC2 is one feature. PC1 captures the most of the data, PC2 captures the next most data. Let's say PC1 captures 90% of the data, PC2 captures 8% of the data. Then what data we are leaving behind is the 2% of the data we are leaving behind. That means you still have significant data to train the model on, right? So yeah, um, we can reduce from 1 million features to just 2 features as well. PC1 covers 98.3% of the variance of the data. PC2 covers 1.5% of the variance of the data. And how much is left behind in this example? Only 0.2% is left behind. So even though we reduced from 1 million features to 2 features, the data we left behind is just 0.2%, 2%, 0.2%, right? And we still get the good model which predicts the outputs for us. So this is the code for principal component analysis and dimensionality reduction. We are saying decrease the components to 4 here, and then we are fitting the data actually. So yeah, you can see over here it covers 99.8% of variance. Only 0.2% of the variance is left behind. Yeah, this is about dimensionality reduction. Any questions on this? And what are the uses of dimensionality reduction? As I said, noise reduction model will be fit perfectly if we have just 2 signals. If you have, let's say, 1 million signals, the model may not fit perfectly because there is a lot of noise with respect to features, right? And then we get speed with dimensionality reduction. So how do we evaluate a classifier, right? Let's say you created a model, classification model, which predicts COVID positive or not, given the patient samples, right? You created the model, but how do you know if the model is predicting properly or not? We need to evaluate the model, right? How do we evaluate the classifier? You can look at the confusion metrics of the classifier to understand how well it is predicting, right? This is an example of confusion metrics plotted for COVID test data. So 24 people, our model predicted as positive, and all those 24 people are really positive. This is true positive. And our model predicted negative for 6 people, but they're actually positive in reality. So total 6 false negatives. And for 10 people, model predicted positive, but in reality, they are not positive. So 10 false positives. For 60 people, model predicted negative, and in reality, they are negative, right? So out of 100, how many mistakes our model made? It's 6 plus 10, 16. And for 84 people, it predicted properly. Right? This is how we look at confusion metrics. So for 84 people, it predicted positive correctly. So our accuracy of the model is 84%. And accuracy is one parameter we look at while evaluating the model, while evaluating the classifier, right? And there is a precision, one other parameter to evaluate the model. So precision, when the model says positive, do we really trust it? Is what determined by prediction, precision, right? So for a good classification model, precision should be high, accuracy should be high, and recall also should be high. So recall is basically of real cases, how many it caught, right? Um, it's true positives divided by true positive plus false negatives. This is the formula for recall. And F1 is the mix of both precision and recall. And F1 also should be high. So for a good classification model, accuracy should be high, and we can't just rely on accuracy. We should check precision, recall, and F1 too, and all of these should be high, right? You can see in the next slide for classification, KNN classification, how our model evaluations are, right? So just a sec. Yeah, here, sorry, for one of the logistic regression model, the accuracy is 0.92 and F1 is 0.91. So we are looking at accuracy and F1. F1 is combination of recall and precision. So if F1 is high and accuracy is high, then our model is doing well, right? That's the idea about evaluating the classification model. The accuracy should be high and then F1 should be high. When F1 is high, that means precision and recall are high, because F1 is a combination mixture of both precision and recall, right? And KNN is K nearest neighbor classification technique. So in this technique, basically model looks at K nearest neighbors in order to predict the output. So you can see in this diagram, so our K is 1. That means we are predicting by looking at the nearest one neighbor. So this is the X test we need to predict. Then the nearest neighbor to the value we need to predict is this red circle. So the X test is predicted as red. Let's say I'm taking k equals to 3. Now our model looks at 3 nearest neighbors, and one of the neighbors is red, and two of the nearest neighbors is blue. So the majority is blue. So our test is classified as blue, right? Over here, we are saying k equals to 4. Then model looks at 4 nearest neighbors in order to classify the test value, right? Since k is 4 here, there is a tie between red and blue. So based on this, it's always better to use the odd number for k, right? And yeah, it tells the same thing. Find the k nearest training points, take vote, right? And it read and KNN requires feature scaling. It's based on distance, so your features needs to be scaled on a scale of 0 to 1 so that the model will predict well. If they're not scaled based on 0 to 1, then the distances for the features will be different and your model may not be able to predict well. So for KNN, scaling is required, right? If you choose a small k, it's very sensitive to noise. If you choose large k, it may underfit, it may not be able to predict well. So we need to tune and find the right k with a technique called cross validation. If our k should be 1, 3, or 5, or 10, how do we decide? We need to use the technique of cross validation to decide the k value, right? That we'll talk in few minutes. And this is the code for k nearest neighbor classifier. Um, it's similar to the previous classifiers or previous models we saw. K neighbors classifier, we are saying number of neighbors is 5, and then we are fitting the data and we are predicting for the test set. And then the classification underscore report function prints precision, recall, and FN score for us to evaluate the model, right? So what is cross validation? We determine the value of k by using cross validation. So how do we do it? This is our total data, right? And we split the data into chunks and train the data on these 3 boxes and test with this 4th box for k equals to 1. Start with k equals to 1, and then you are splitting your data into four paths, and you train on 3 paths and test on the 4th part. For the second iteration, you are selecting this 3rd set as a training set. Then you train on set 1, set 2, and set 4, and test on set 3. For the 3rd iteration, you test with set 2. For the 4th iteration, you test with set 0, right? And then take the average. And then take the average and decide the k value, right? This is how we do cross validation in order to decide the k value. Um, any questions there, or is this clear? So we start with K1. We split the data into 4 parts, and then we do 4 iterations for K equals to 1, right? For the first iteration, you take the fourth set as a test set. You train on the remaining 3 sets and test on the fourth set. For the second iteration, you test on the third set, train on the remaining sets. And at the end, whatever the E value you take the average of the value. And then you keep the average for K equals to 1. Then repeat the process for K equals to 3. Get the average. Then repeat the process for K equals to 5. Get the average. At the end, let's say you were testing from K equals to 1 to K equals to 10. Once your process is done, you have this average value for each K value. Whichever average value, just a sec, how to see. Best mean CB square. Yeah, whatever is the average very near to mean, you choose that K as your K nearest neighbor in order to train the model. Right. So this is about finding out the K with the cross validation technique. Right. And then logistic regression. Logistic regression is to solve the binary classification problem. Right. If you remember in lesson, I think in lesson 1, we discussed about binary classification, where if you have an email, you need to predict whether the email is spam or not, whether it's COVID positive or not. So for these kind of binary classifications, we use logistic regression to solve the problem. Right. And the formula is the same. Formula is similar to linear regression. B0 is the constant or bias. B1 is the weight. B2 is the weight for feature 2. B1 is the weight for feature 1. And then it's B1 x1 plus B2 x2 plus B0. And then you apply the sigmoid function over this Z in order to get a binary output or binary classification result, right? So if the value of the sigmoid function is large positive value, then it is close to 1. If the value is large negative value, it is close to 0. Then the value is near to 0, it is close to 0.5. I can show you the sigmoid function graph. So this is a sigmoid function graph. If the value is negative, it is close to 0. Value is positive, it is close to 1. If the value is near 0, it is 0.5. This is the sigmoid function on y-axis. And on the x-axis, the z is there, right? For positive, the value should be close to 1. For negative, value should be close to 0. Based on the probability, it will classify whether positive or not, right? If it is greater than 0.5, then it's positive. If it is less than 0.5, then it's negative. Let's say if we are classifying for disease positive or not, then if the probability is greater than 0.5, then it's positive. If the probability is less than 0.5, then it's negative. Right? Yeah, the same thing is mentioned here. And how the weights are calculated. I think this is an important concept. So we start with random weights and apply the gradient descent to find the minimum error. We repeat this process while adjusting the weights and check the error. We repeat the process until the error is minimum. Once the error is minimum, we finalize the weights. That is the process of calculating the weights, right? Probably you can explore more on this in order to understand better. So the gradient descent is basically we adjust the weights and calculate the loss. Let's say loss is 0.8. Then you adjust the weights again. Then calculate the loss. Let's say loss is coming until 0.1. And now for the next 3 iterations, the loss is still 0.1, right? Then you stop there and then say these are the weights where the loss is minimum, right? And that's how you choose the weights. Yeah, that's about linear regression model. How do we evaluate how do we evaluate the binary classifier or the logistic regression? It's the same process. We use accuracy, precision, recall, and F1 score. Ideally, accuracy and F1 score are enough to validate the classification model, right? Yeah, that's about logistic regression. Um, so here, preventing overfitting. I think we add on number of features in order to prevent from overfitting. Yeah, you can basically check this. So that's all for week 3. We discussed about pre-processing, where for numerical features, you can apply min-max scaling. You scale between 0 and 1, and then you apply standard scalar, which is with mean and standard deviation. And then for categorical data, we looked at one-hot encoding. Then we looked at a processing technique called PCA, principal component analysis, where we where we dimensionality reduction from 1 million features to 2 features, but without reducing, which covers the maximum variance. We covered 98.2, 99.8% of the data, but still we are able to reduce from 1 million to 2 features, right? We looked at principal component analysis, and then classifier evolution. These are the metrics we use for classifier evolution, confusion metrics, and precision and F1. Precision should be high, F1 should be high for a best classification model. We talked about k nearest neighbor. If our k is 3, in order to predict the test value, it look at the 3 nearest neighbors, and if two neighbors are red and one neighbor is yellow, then the predicted value is red, right? That's about k nearest neighbor. But how do we choose k? For that, you need to do cross validation to choose k. You start with k1 and then 3, then change it to 5, 7, and 10 or 11. And you split your data into 4 chunks or 5 chunks, and then repeat the process for k equals to 1 for all the 5 chunks. Every time, take one chunk as a test data, remaining chunks as a train data, and get the average mean for k equals to 1 up to k equals to 10 or 11. And for whichever k the average mean is near to the mean, you take k as that value. Right? That is about cross-validation to find out k. And then logistic regression, we apply a sigmoid function to the target value in order to convert the value between 0 and 1. And if the probability is greater than 0.5, then we categorize it as positive. If the probability is less than 0.5, we categorize as negative. Right. Yeah, that's about today's class. And in the next class, we discuss about deep learning and convolutional neural networks. So